Okay, so rate of reaction. Rate of reaction is the topic. Rate of reaction. Okay, so you need to understand what's happening to the rate of a reaction during as the reaction proceeds. So when is a reaction at its quickest rate, at its fastest rate? At the start of reaction. At the start of a reaction is when the reaction is at its quickest, at its fastest rate. Okay, so why is that? So the reaction is fastest, quickest at the start. Why? Because the concentration of the reactants is the highest. Okay, so when you first start, the second you start the reaction, you've got a lot of reactants in there. So it's going to be very fast right at the start because there's lots of reactants. Okay, then as the reaction proceeds, what happens to the rate? So as the reaction proceeds, what then happens to the rate from that starting point? So starting point very, very fast. As the reaction proceeds, what's going to happen to the rate? So the rate of reaction will slow down. The rate of reaction slows down. Why? Because the concentration of the reactants decreases. The concentration of the reactants decreases. Okay, so it's fastest right at the start, then from then on it's slowing down until finally at the end of the reaction, what happens at the end of the reaction? At the end of the reaction, when one of the reactants have been used up, it doesn't have to be both of them, when one of the reactants has been used up, the rate of reaction will be what? The rate will be 0. There'll be no reaction. It'll have stopped. Okay, so if you were to plot this, so if we were to do an experiment, maybe something like, I don't know, like say if we were to take some calcium carbonate and hydrochloric acid, and we were to do this reaction, we get calcium chloride, salt, plus carbon dioxide gas, plus water liquid. All right, we do this reaction, and we want to monitor the rate of reaction, and we're going to collect the gas. So volume of gas produced or measured, volume of gas produced in centimeters cubed. Over time, we're going to set a clock, and we're going to do the time in seconds, and we're going to plot at the rate of which volume is being the carbon dioxide is being produced. So initially, at time zero, there's no carbon dioxide, and the reaction is the quickest, the fastest, right at the start. When you've got a lot of reactants, the concentration of the reactions is high. So it's going to be very steep, it's going to be very fast, but then it's going to slow down as reactants get used up. It's going to slow down, and then eventually it is just going to go horizontal. So there's going to be no change in the volume of gas produced over time because the reaction is over. So initially at the start, it's a very fast rate, a fast reaction at the start. Then it starts to slow down, and then eventually reaction is over when it goes horizontal and no more carbon dioxide gas is being collected. So this is if we had a gas syringe and we were collecting the carbon dioxide gas in a gas syringe, and we were measuring the amount of carbon dioxide gas collected. Okay, so the rate of reaction can be found if you draw a tangent at various points, tangent to the line. If you draw a tangent and find the gradient of the tangent, then that's how you can work out the rate. If it's a fast rate, it's steep, and then a slower rate, it is not as steep. Okay, we need to define rate of reaction. So how do we define it? Rate of reaction is a change in concentration, right? You can use amount, you can use volume, like volume of a gas, but I'm just going to put change in concentration over time, measuring how something is changing over time. Therefore, the units are going to be concentration is moles per decimeter cubed, and time could be seconds to the -1 because it's over time, or minutes to the -1, and that's the units of rate. Okay, for AS chemistry, for OCR AS chemistry, it is a very qualitative approach to rate. For second year, for A2, you've got to do a more quantitative approach where you've got to do lots of calculations. Okay, so that's just a start, introduction to rate of reaction. So, why does a reaction actually happen in the first place? You know, what's happening so that a reaction can happen? So the molecules, the particles, they first need to collide. Okay, there's something called the collision theory, and you need to know what the collision theory is. Okay, so for a reaction to happen, the collision theory. So a reaction can only take place. A reaction can only take place. Sorry, my writing's not very good. Can only take place when molecules collide. Which makes sense. We've just done bond enthalpy. So we know that molecules, they collide and bonds have to break. The molecules collide. So collide. But they've got to collide with sufficient energy. So that's with enough energy, with sufficient energy to overcome the activation energy. To overcome the activation energy. Okay, so a reaction can only take place when molecules collide with a sufficient energy to overcome the activation energy. So remember the activation energy? Remember what that is? That's the minimum energy, min energy needed for a reaction to take place. Okay, so the molecules have to collide, but a lot of the molecules collide and just bounce off each other because they're not colliding with enough energy. If the two molecules collide with enough energy, then a reaction will take place, and that energy is the activation energy. And also they need to collide in the correct orientation. Okay, so we're just going to be, so I'm going to lose the full stop and just go and the molecules must collide in the correct orientation. And what does that mean? Orientation. In the correct orientation. It just means the right way round. Just collide the right way round. Okay? That's a collision theory. So for a reaction to take place, the molecules must collide with enough energy, it's energy to break the bonds. It's called the activation energy, and it must be the right way round. Otherwise, a reaction doesn't happen. So if you think about in a container, you're doing a chemical reaction in a container. A lot of the molecules colliding are not reacting; they're just bouncing off each other, bouncing off the walls of the container. In order for a reaction to happen, collide with enough energy to break the bonds. All right. So what factors affect the rate of reaction? What actually affects the rate of reaction? Okay. Factors that affect the rate of reaction. What are they? And why? Got to say why as well. Okay, why as well. Okay, factors affect the rate of reaction. So first, what have we got? Let's say surface area first of a solid. Surface area of a solid. Okay, factor that affects the rate of reaction. Why? Why does that affect? So if you have a powder, a powder has a, what kind of surface area does a powder have? Has a large surface area, A powder has a large surface area, because if you think about it, if you've got a lump and you've got lumps, and then you've got some acid in your container, you've got some acid, and the acid is just going to react with the outside of the surface area of the solid. Whereas if you've got a powder in your acid, then the surface area is a lot greater, and therefore the rate of reaction will be faster. So a powder has a larger surface area, which means that there's going to be a faster reaction. Or a lump has or vice versa. Okay, so that's surface area of a solid. What else affects the rate of reaction? What other factors? So concentration of a solution can affect the rate of reaction. But why? Why? So if you have a higher concentration, okay, so say if you have, for example, you have 5 moles per decimeter cubed instead of 1 mole per decimeter cubed. You've got 5. You've got a higher concentration. So that means there's more moles. That means that there's 5 moles. There's more amount of substance in 1 decimeter cubed, whereas this has 1 mole in 1 decimeter cubed. Okay, so there's more moles, more amounts. So this means that the molecules are closer together. In the higher concentration, the molecules are closer together. So if they're closer together, therefore the collisions are more frequent. Collisions are more frequent if they're closer together. Collisions are more frequent, and therefore the rate of reaction will increase. Okay, the rate of reaction, because there's going to be more frequent collisions. And the key word there is frequent. Molecules are closer together, so there's more frequent collisions. Okay, now the other one is pressure. And pressure's got a really similar answer. So pressure affects the rate of reaction, but it's a really similar answer to concentration, because pressure and concentration are directly proportional to each other. So another factor that affects the rate of reaction is the pressure of a gas. Okay, and pressure and concentration, they're directly proportional to each other of a gas. The pressure of a gas. Okay, so if you have a gas syringe, okay, I'm not very good at drawing gas syringes. Here we go. If you have a gas syringe and you've got a gas in there, you've got to get your gas in there. Okay, if we increase the pressure, that means increase the pressure and putting the gas into a smaller volume. Okay, we push it in and we put it into a smaller volume. We increase the pressure. How is that going to affect the rate of reaction if we increase the pressure? So if you increase the pressure, the molecules are pushed closer together. They're in a smaller volume. The molecules are pushed closer together. They're in a smaller volume, and therefore there's more collisions. Therefore, we missed a word. Therefore, more frequent collisions, because they're closer together, more frequent collisions, and therefore the rate of reaction will increase. Therefore, the rate of reaction will increase. Okay, right, so for OCR AS chemistry, we're not going to talk about those in any more depth. Surface area of a solid, concentration of a solution, pressure of a gas, we're not going to talk about those in any more depth. The 2 other factors we have to talk about in a bit more depth, okay? So the first factor is the temperature. And the next factor, the last one is, you probably hopefully guessed, is catalyst. Okay, so those 2, we're going to talk about them in a little bit more depth. Okay, how how does changing the temperature affect the rate of reaction? How does using a catalyst affect the rate of reaction? Okay, now in order to talk about, we're going to do temperature first. In order to do that, we need something called a Boltzmann distribution. Okay, now be careful with your spelling here. A Boltzmann distribution. So that's B-O-L-T-Z-M-A-N-N. Right, now what's a Boltzmann distribution? So Boltzmann distribution shows you the distribution, the range of energies of molecules at particular temperatures. Okay, so what does this show you? It shows you the distribution, the range, so the distribution, the spread of energies of molecules at a particular temperature. Okay, it's called a Boltzmann distribution, right? So, okay, how do you draw it? So you need to draw your axes first, right? And on the y-axis here, it's labeled number of molecules with given energy. Number of molecules with given energy. Okay, and on the bottom axis, it's just labeled energy. All right. So if you take a container, you take a sample, there are 0 molecules with 0 energy. Okay, all molecules have got some energy. And if we're looking at the spread of energy, and the shape is really, you've got to do the shape really carefully. It goes quite steep, and then you curve off like that, and then you do not touch the x-axis like that. That's a distribution, that's a Boltzmann distribution. Okay? And the reason why we don't touch the x-axis is there is no maximum energy for a molecule. There is no maximum energy for a molecule in a reaction. No maximum energy for a molecule. Okay, right. And then the area underneath, yeah, the area underneath the curve. The area underneath the curve represents the total number of molecules in the sample. Total number of molecules in the sample, in the reaction, whatever you're doing. Okay, so you can see the majority, most molecules have just got a medium kind of energy. A few molecules have got a lot of energy, and a few molecules have got not much energy. So just a spread, distribution of energy of molecules in a reaction. Now we're going to label on here the activation energy. It's going to be up here somewhere, the activation energy, EA. All right. So remember what we said. For a reaction to occur, the molecules need the minimum activation energy. So if we were to shade in this region here, to colour in that region there, okay, and what we can say is that region there that was shaded in, so these molecules, it's these molecules which have energy greater or equal than the activation energy, can react, and therefore that's a successful collision. So of all the molecules in the sample, it's just these molecules that have got energy greater or equal to the activation energy. Now when they collide, that's going to lead, that's a successful collision, that's going to lead to a reaction. So it's just these molecules. All of these molecules, when they collide, they just bounce off each other and go and collide somewhere else. Okay, and this is called a Boltzmann distribution. And when we want to look at how temperature affects the rate of reaction, we need to use a Boltzmann distribution, right? So I'm just going to quickly draw. So this is looking at the effect of temperature on the rate of reaction, looking at the effect of temperature, okay? So I'm just going to quickly draw the Boltzmann distribution again. Don't forget your axes. Number of molecules with a given energy. Okay, there's no units because we're not actually putting numbers on there. Number of molecules with a given energy versus energy. Okay, get your shape, so nice and steep, and then curl off, and then come, was a bit of a shape there. Okay, oh, there we go, okay, like that. Okay, that's the Boltzmann distribution. Let's label on the activation energy, like that, and that's a Boltzmann distribution. So what happens when you increase the temperature? So I'm going to write here, increase the temperature. Okay, what happens to the energy of the molecules when you increase the temperature? So the molecules have got more energy, haven't they? More kinetic energy if you increase the temperature. So what happens is this shape changes when you increase the temperature. The molecules have got more energy, and it changes, and it kind of becomes lower, kind of flatter, spreads out more. The area should be the same. The total area is the same. So the total area is the same because you haven't got any more molecules. So the total area is still the same. But now the maximum is lower and to the right because the energy of the molecules is spread out. Okay, so I'm going to label this as the higher temperature. This is a higher temperature. Okay, so activation energy doesn't change. That's still exactly the same as the activation energy. But look what we can see now. We now have the shaded area, more molecules, let's write this down, more molecules have energy greater than or equal to the activation energy. Therefore, there will be more successful collisions in a certain time period. Therefore, the rate will increase. And that is how temperature affects the rate of reaction. Because the energy is more spread out, the distribution of molecules more spread out at a higher temperature, there's more molecules with energy greater than the activation energy. What's going to happen at a lower temperature? At a lower temperature, the energy, there's going to be less energy. So a lower temperature, you could do with a different coloured pen ideally here, different coloured pen. Lower temperature, it's going to be taller, steeper, and to the left. And still it's not going to touch, the area is still going to be the same. At a lower temperature, the maximum is higher and to the left of the original. And now you can see, okay, I could do with a different colour pen, I'll do wiggly lines. Now you can see that there are fewer molecules with energy greater than the activation energy. So there'll be fewer collisions and a slower rate of reaction. So that is how temperature affects the rate of reaction, and that's what you need to be able to explain. Now finally, before we finish, let's quickly do catalyst. Okay, nearly finished. Catalyst, how does a catalyst affect the rate of reaction? Okay, so first you need a definition of a catalyst, all right? What's the definition of a catalyst? Okay, how does a catalyst affect the rate of reaction? We need the definition of a catalyst. So a catalyst speeds up the rate of reaction. Yeah, speeds up rate of reaction without being used up. Okay, that's all right for GCSE, being used up. Oops, not good enough for A level. Okay, you need to say speeds up rate of reaction without being used up. And how does it do this? It provides, a catalyst provides an alternative route of lower activation energy. That's how it does it. Okay, so if we take an enthalpy profile diagram, okay, an enthalpy profile diagram with enthalpy here and progress of reaction here. Okay, and I'm going to put reactants, whatever the reactants are there. I'm going to put products there. What type of enthalpy profile diagram have I drawn here? Drawn an exothermic. Okay, and then remember delta H from the reactants to the products, delta H. Activation energy from the reactants to the top activation energy. So that's an enthalpy profile diagram. Okay, now a catalyst speeds up a reaction without being used up. It provides an alternative route of lower activation energy. So it provides an alternative pathway, an alternative route of lower activation energy. So still starting and ending, but the lower activation energy. So I'm just going to put it there. It's a bit confusing. I'm going to put EA cat. Okay, I'm just going to put EA cat like that. And it's a lower activation energy, and that's how a catalyst speeds up a reaction. Right, in terms of the Boltzmann distribution now, let's have a look at the Boltzmann distribution. We need to be able to explain it in terms of the distribution of energies of molecules. So we've got to do the axes again. Number of molecules. You can just leave it as number of molecules, but let's put the whole thing in. With a given energy. With a given energy. Okay, versus energy. Now be careful with your shape. I'm going to take a bit more care with my shape this time. So steep, and then do it like that, and then calm down. Don't touch the x-axis. You draw on activation energy. Okay, and that's your Boltzmann distribution. Okay, and how does a catalyst affect? Well, a catalyst offers a lower activation energy, an alternative route of lower activation energy, EA cat. So now we can see the area underneath the curve, that now, compared with previously, there are more molecules with energy greater than or equal to the activation energy. Therefore, there will be more successful collisions. Therefore, the rate of reaction will increase. Okay, and that's how you explain how a catalyst speeds up a reaction.